Okay, in this video, we're going to talk about directional derivatives, really big topic in 17C. But first, we have to have a quick review of some 17B topics, just because they're going to come up pretty quickly and want to make sure everybody understands. So in 17B, towards the end, we talked about the dot product of two vectors. If I took a vector u and a vector v and put them tail to tail, if they're not parallel, there's an angle between them. And the dot product is defined to be the magnitude of u. Remember, this notation means magnitude. That's the length of u, the length of v, times the cosine of the angle between them. And remember, because the dot product involves the cosine, if the cosine of 90 degrees or pi over 2 is 0, you'll get a dot product of 0. And that was one way to tell that two vectors were perpendicular, right, if their dot product was 0. So this is the definition of the dot product. And then we figured out a way to find the dot product of two vectors without actually knowing the cosine of the angle between them. And so if I had two vectors, A, B, and C, D, the dot product we found out was actually going to be AC plus B times D. That is not good there. Okay. So you multiply the x values and add what you get when you get the y values, the y component of your vector. Okay, so for example, if I had u equaling 1, 4, so that vector would be over 1, up 4, 5, 2 for v is over 5, up 2. So there's definitely an angle between them, but we don't need to know it. The dot product of u times v is 1 times 5 plus 4 times 2, which is 13. Okay. We also maybe didn't spend quite as much time on this, but this is going to come up too. Writing the equation of a line, particularly in three-dimensional space, we already have a way to do this in two-dimensional space. But in three-dimensional space, the way we write equations of lines is we use a parameter. Okay, so we're going to do this for just a two-dimensional line. Let's say I have a line going through 1, 2, and 4, 7. So the way to do this is you're writing x and y separately, and it's helpful for me to think about a particle moving along this line at a constant speed. And so let's say the particle is right here at t equals 0, and 1 unit of time later, it's at 4, 7. So then if you think about that, then your x coordinate was 1 at the beginning, and in 1 second, notice it increased by 3, right? 1 plus 4. And it would make sense that if it's moving at a constant speed, every second, your x coordinate's just going to get multiplied by 3, right? You're going to get 3 extra units on your x value. So it's 1 plus 3t. Similarly, my y value starts at 2, and in that 1 second gained 5, and it'll do that every unit of time. It's going to gain 5 times each second. So you can write the equation of a line as x equals 1 plus 3t, y equals 2 plus 5t, and as long as you allow t to be any number between negative infinity to positive infinity, you can generate every single point on that line with that parameterization. Okay, so here's what we mean by a directional derivative. On an earlier video on partial derivatives, I introduced that using this function, 9 minus x squared minus y squared, because it looks like a mountain. Okay, it's an upside down paraboloid and it's easy to visualize. So we had this surface and we were talking about a specific point on the side of the mountain, 1, 2, 4, which I included the level curve for that point, which would be at z equals 4, would be a circle, just so we could visualize this, okay? Now, what we're going to do here is let's imagine a top view. If you were looking down from above on the z-axis and you were looking down, you would see this blue circle, right? That's at a z value of 4. This is, remember, with z values or level curves, we sometimes call them k. And remember, the summit of the mountain would be right here, right? That's right over the origin, is the summit of the mountain. Now, with partial derivatives, what we talked about before, that's giving you the slope. If you want to find the slope in the x direction, from 1, 2, you would move in the x direction. You would go this way along the positive x-axis. Whatever that slope is what we mean by f sub x. That's your partial derivative with respect to x. And if you moved in the y direction, you could find the slope of your graph using your partial derivative with respect to y. But what we are now going to have the ability to do, what if you're on the side of a mountain here, you should have more options than moving just in the x or in the y direction. Say we want to move in this direction, and one way to specify a direction is with a vector, right? So this vector I'm using here is 4/5, 3/5. That's the reason it's a fraction is because this is a unit vector. The magnitude of that vector is 1. But that gives us a direction, right? Over 4/5, up 3/5. So we're going to move in this direction of this vector u. Now, hopefully you can kind of tell, go back to the three-dimensional graph. If you move away, remember the summit of the mountain is right there. This is the top. You're kind of moving away. So hopefully you can see that you'd probably be going downhill, right? If you move in this direction. We'll confirm that when we do it. So here's how the formula is derived. Just a little bit of theory here. If we wrote the equation of a line right here, if we parameterize this line, we know it's passing through 1, 2, and we know it's moving in the direction of u. And so we know in the x direction, it's going to gain 4/5, and in the y direction, it's going to gain 3/5. So my line is going to have this parameterization. X is 1 plus 4/5 t, y is 2 plus 3/5 t. Okay, now what we want is the slope of the function in the direction of this line, right? In the direction of this tangent line. But now we have written our line as a function of t. So our original function is a function of x and y, but now both x and y are functions of t. So you see where we're going with this. This is the chain rule. This is what we talked about in the previous section of the book. So if I want to know how the function's changing with respect to t, I have to follow my chain rule mapping. Partial of f with respect to x times dx dt plus the partial of f with respect to y times dy dt. Now, because we reviewed the dot product, another way to think of this chain rule, you can actually think of this as a dot product, right? If I took partial of f with respect to x, partial of f with respect to y, and dotted it with dx dt, dy dt, remember how you do a dot product? It's this times this, which is right there, plus this times this, which is right there. So that works, right? It can be thought of as a dot product of two vectors, where one of them is made up of your two partial derivatives. And we're always going to do this when we want the directional derivative. So we're going to give this a special name. The vector that's made up of your two partial derivatives, we denote it as it's an upside down triangle f with a vector sign, and that's called the gradient. Okay, so this is the gradient vector, is that one right there. Dotted with, now notice dx dt and dy dt. I'm going to slide this back up here. You get 4/5 and 3/5. But what was 4/5 and 3/5? That was just our original vector u. And that's always going to happen as well. So this leads to our formula. If we want the derivative of f in the direction of some vector u, as long as u is a unit vector, okay, and the notation is that is d subscript uf, the derivative of your function in the direction of u. It's the gradient of f dotted with u. Okay, this is our big formula. Let me show you how this works. Okay, so here we go. We've got, this was our mountain equation. Our gradient vector made up of your two partial derivatives is just -2x, -2y. And I would want to evaluate it at my point. We were at the point 1, 2. So if I plug that in for x and y, I get -2, -4. And so the slope of our function at that point in the direction of that unit vector is going to be the gradient dotted with u. And that's really easy, right? -2 times 4/5 plus -4 times 3/5 gives me -8/5 minus 12/5 is really -20/5, right? Which is the same as -4. Now, why should that answer not surprise us? Earlier, we were visualizing it and we thought we would probably go downhill, right, if we moved in that direction. And sure enough, the fact that that answer is negative means that your slope is negative, so you are going downhill, okay? Let's try just to see another one. Let's say we're at that same point, but now we're going to move in a direction this way. And so I just made up -3, -1, right, as a vector, v. Remember, the top of the mountain is right there, okay? So we are kind of moving not directly towards the top, but we are moving in a direction close to the top. So I'm expecting we're going to go uphill, right? If you remember what the graph looks like, I'm expecting a positive answer here. Okay, the one thing with the formula, it's the gradient of f dotted with u. U has to be a unit vector, meaning the magnitude of our vector has to be 1. So this is, I guess, more 17b review. The term they use to make a vector a unit vector is to normalize it. It's kind of a strange word, but that just means you're making a unit vector in the same direction as v. It's very easy to do. You just do 1 over the magnitude of v times v. Remember, the magnitude of a vector is just the square root of each part squared added together. And then times my vector. I get 1 over root 10 times my vector, and I'm just going to distribute that. And I get -3 root 10 over root 10, -1 over root 10. So that's a vector that's just 1 unit long going in the same direction, okay? And that's all I need. Then I'll dot that unit vector with, I already worked out my gradient on the previous example, and that gives me 6 over root 10 plus 4 over root 10, which is 10 over root 10. And again, the interpretation, that's positive, which makes sense. We're going to be going uphill if we move in that direction. Okay, let's look at another example with a whole different function. This time we won't have the luxury of knowing what the graph of the function looks like. We won't, very rarely will we be able to know what some of these three-dimensional graphs look like. So, I mean, you can if you use a computer, but we're not going to. Okay, so here's my function. Coincidentally, we use the same point. And here's our unit. Notice this is already a unit vector. Why? Because the square root of 5 over 13 squared plus 12 over 13 squared. You can check it out, but you're going to get 1 out of that. So this is already a unit vector. Okay, so that's good. So all we need to do is find the gradient. That's the partial with respect to x is 5y squared. Partial with respect to y is right there, -8xy. We want to evaluate our gradient at our point, which is at 1, 2. So plugging in 2 for y, 1 for x, I get 20 and -16. And then if we want to find the rate of change of our function in the direction of the vector u, we're just going to dot our gradient vector with u. That gives me 100 over 13 minus 192 over 13. So I get an answer of -92 over 13. So the function's decreasing, right? It means if you want to think of it as a mountain, you're going downhill, right? And then one more example, kind of just from beginning to end, to show you that these really aren't that bad. I want to find, this is number 11 in 9.5. Our function is 1 plus 2x over, 2x times root y at 3, 4 in the direction of the vector 4, -3. Probably a good idea, I should have done this, pause the video, see if you can work it out and get the final answer. Okay. Assuming you've done that. So step number one, so sometimes they'll give you, the vector they give you is a unit vector, sometimes it's not. So if it's not, then you do have to normalize it. So we're going to do 1 over the magnitude times v. The magnitude is the square root of 4 squared plus negative 3 squared. That gives me, that's 5 actually. This is 25, square root of 25 is 5. If I distribute the 5, I get 4/5, negative 3/5. My gradient, f sub x, f sub y. Make sure you can get those two answers. And then of course you do want it evaluated at your point. So that's going to give me 4 3/2. And then I just dot my gradient with my normal vector, and I got 23/10. Oh yeah, sometimes our book, I mean, they have to give you some kind of a direction. Usually it's with a vector, but in this example, they wanted the directional derivative at a point. Another way to assign direction, I suppose, if you're thinking in the xy plane, is to give an angle, right? Say, I'm at some point and I want to move at an angle of 2 pi over 3 from where we are, from 0, 4. So this is, but you can use that information to get a vector. If you refresh your trig a little bit, at 2 pi over 3, you're going to be left with a pi over 3 reference angle. And if you use the unit circle, okay, the unit circle, the coordinates on there are actually, if you turn this into a vector, negative 1/2 root 3 over 2, that's actually already a unit vector, okay, because it's a unit circle, right? I already know that squared plus that squared has to give me 1 if you think on the unit circle. Okay, so the only difference here, I guess, is you have to use that angle to get a vector that's pointing in the same direction. And then it's all the same. Okay, find your gradient vector from your two partial derivatives, evaluate it at 0, 4, and then dot it with your vector that you found. And I get 2 plus root 3 over 2. Okay, last example, I think you need to also be able to view a directional derivative. Now that you know what it is, okay, a lot of times you're not going to be given a function. Okay, a lot of times the way to think about directional derivatives are from a contour plot, okay, and knowing how to read a contour plot, okay. So what I have here are a bunch of, okay, this is actually a topological map. Many of you have probably seen that if you ever look at a topological map when you go hiking. It gives you lines of elevation, right? This is also a contour plot. It's a contour plot of the region you're hiking in, of the Earth, okay? So you can tell these are all the points that have an elevation of 400 feet, 300 feet, 200 feet, 100 feet, and so forth. Okay, now if I've got a scale here from 0 to 4 miles, the question is, we're going to estimate the value of the directional derivative from point A to point B. Imagine you were going to go hiking and you were going to go from here to here. The derivative is slope. Okay, it is the slope. Now, you don't need to do a gradient. You don't need to do a vector or anything. All the derivative is just how much does your elevation change, how much does your function change, divided by how far you're moving, right? How far is this? So if you, at point A is at an elevation of 100 feet, and we're moving towards point B, which is at an elevation of 300 feet. So we have a change of elevation of 200 feet. And using our scale, if you think about that distance is roughly the same as 2 miles, right? That distance is roughly the same. So I'm gaining 200 feet in 2 miles. That means my derivative, which is my rate of change, is about 100 feet per mile, right? Each mile I walk, I can expect to climb about 100 feet. Okay. In the next video, we're going to talk about some special properties of the gradient vector.